Welcome to using the Wronskian. So recall, for equation or for solutions, y1, y2 of y double prime plus p of x y prime plus q of x y equals 0 on open interval AB with p and q continuous on AB, that we had y1 and y2 form a fundamental set of solutions. On AB, if and only if the Wronskian which was y1 times y2 prime minus y1 prime times y2 is non-zero anywhere on AB. So is non-zero anywhere on AB. We also saw that if it was non-zero somewhere on AB, it was non-zero everywhere on AB. So we can again use this fact to check if we have a fundamental set of solutions. So let's go ahead and consider the differential equation x squared y double prime plus 3xy prime minus 3y equals 0. And let's verify first that y1 equals x and y2 equals 1 over x cubed are solutions. And then we'll use the Wronskian to show they form a fundamental set of solutions on both negative infinity to 0 and 0 to infinity. So first thing we need to do is just check their solutions. So y1 equals x, then y1 prime is 1, and y1 double prime is 0. And we have x squared times y1 double prime plus 3x times y1 prime minus 3 times y1 is therefore equal to x squared times 0 plus 3x times 1 minus 3 times x. And this just becomes 3x minus 3x. This is indeed 0. Similarly for y2. Y2 is, I'm going to do this with negative exponents, x to the negative 3. That means y2 prime is negative 3x to the negative 4. And y2 double prime would therefore be 12x to the negative 5. Plugging this in, we have x squared times y2 double prime plus 3x times y2 prime minus 3y2 would be equal to x squared times 12x to the negative 5th plus 3x times negative 3x to the negative 4th minus 3 times x to the negative 3. Well, these are all set, so when we multiply the exponents, we just wind up with x to the negative 3. So we have 12x to the negative 3 minus 9x to the negative 3 minus 3x to the negative 3. And that is indeed equal to 0. So we know these are both solutions. Then to check the Wronskian of y1, y2, we're looking at x and then x to the negative 3 y1, y2. We do y1 times y2 prime. So y1 is x times negative 3, x to the negative 4th. And then we subtract off y1 prime times y2. I apologize, my screen's not updating. Right, so we have the Wronskian of y1, y2, who's y1 times y2 prime minus y1 prime times y2. So I'm just plugging in x and x to the negative 3rd below that. So y1 was x, y2 prime was negative 3, x to the negative 4. And we are subtracting off y1 prime was 1, y2 was x to the negative 3. So the Wronskian is negative 3, x to the negative 3 minus x to the negative 3, or negative 4x to the negative 3. All we have to do is check that this is non-zero at some point. So this is non-zero everywhere except at x equals 0. So this is non-zero on negative infinity to 0 and on 0 to infinity. And so we have a fundamental set of solutions on both intervals. So y1, y2 form a fundamental set of solutions. So this is one use of the Wronskian. An alternative use of the Wronskian here, or way of finding the Wronskian, if we have a differential equation, we can actually find the formula of the Wronskian without knowing the solutions, as long as we know the Wronskian of those solutions at one point. So let's go ahead and find the Wronskian of a set y1, y2 of solutions to y double prime plus 2xy prime minus 3y equals 0, given that w of 0 equals 2. So for this, we're going to have to use Abel's formula, since we don't actually know y1 and y2. So we will use Abel's formula. Which stated that the Wronskian at any point was equal to the Wronskian at a specific point, x naught, times e to the negative integral from x naught to x of p of t dt. So we have all the information we need for that. So in this case, we will use x naught equaling 0. So this is x naught equals 0. Our p of t, our formula is in standard form. We don't have anything multiplying y double prime. So our p of t is 2x. So what we have is, in this case, w of x is equal to w of 0 times e to the negative integral from 0 to x of 2t dt. W of 0 was equal to 2. Then we have times e to the negative integral from 0 to x of 2t is equal to. So we would have integral from 0 to x of 2t dt. This becomes t squared evaluated from z to x, and we just get x squared minus 0, or x squared. So our Wronskian becomes 2e to the negative x squared, which is, of course, non-zero everywhere. But this is how we can use Abel's formula to find the Wronskian of a set of solutions just based off of knowing the Wronskian at one point.